it's on now? Yeah, okay, great. Thanks for the introduction, André. Yeah, indeed, we work in a industry with very sensitive data and which also has a huge potential to generate value when applying AI. So we're navigating a lot of difficult privacy challenges, but actually we love navigating privacy challenges. So yeah, OASYS Now, it's a clinical trial recruitment platform, which is the perfect use case for these large language models, which after this talk you'll see why. And a real world evidence platform. I think, was it Niels that mentioned that there are these like emerging markets and companies for orchestrating data sets? That's essentially what we are doing, but then in the life sciences industry. And we are patient first, which really sets us apart. We actually include the patient in the data governance. We pay a lot of attention to data subject rights. We are privacy by design. We leverage very advanced cybersecurity techniques for that as well. And AI enabled, which is super relevant for today. And yeah, we do GDPR compliance, ISO 27001 compliance, and do it all like in an automated and high-tech and AI-driven way. And we won Dutch privacy awards, I think also from the Dutch DPA institution related to them, yeah. So that's a little bit of small teaser about the company, but first I'll tell you what to expect about this deep dive today. So yeah, I'll first introduce a little bit more about the company and about ourselves, like who's talking to you today. What is AI? Like, what is it? But also a little bit of like a historical background that Nima will tell. We've heard it's been around for decades, so why are we like talking about it now so much and not before? And then what I wanted to do today for the deep dive is look at it in a very practical way, sort of show to you guys how do we technically achieve all of these compliance measures. So maybe you can draw some inspiration and see for your clients like, oh, this is the way that they are doing it. Maybe we can also use that. So how to achieve transparency and explainability, right? We're talking about this AI literacy. We need to be transparent about that. We're using AI. Okay, cool. How do you actually do that in practice in your product? Accuracy and robustness. You want these systems to be trustworthy, but yeah, they always give different results. If you ask the same question to ChatGPT every time, it says something else. So how do you make it robust and say the same thing every time? It's not trivial at all. And privacy and security. So that's sort of the cherry on the pie and my favorite topic. So I'll save the best for last. So before I continue, I just wanted to say, I think it's fun if we can make this interactive. So if you have questions, like what you want to know about AI, try my best together to answer any questions. Does anyone have anything in mind of like, oh, this is what I really want to know today, or some technical question I want to learn? All right, if something pops up during the session, just let me know. So introducing about our company and why we exist. And I'll also show the team and share a little bit more personal background. So our mission in the company is to make personalized health accessible for everyone. So what we're thinking is, you see personalization in so many fields. Like for example, Netflix knows you so well, knows like what you want to watch. But in healthcare, you don't have that. Healthcare doesn't know what you need. And why is that the case? Well, Netflix knows your viewer data, but the healthcare system doesn't know your health data, your health profile, because it's so sensitive. But it would be great if we could actually get the right care to the right person. So that's what we want to achieve. Because we think if we give patients control over their health data, that endless possibilities are unlocked. People can discover what health options fit them, including clinical trials, which is our primary focus right now. If they have agency over their data, they can also choose to give the permission to share to research. So those were those permission rights we were talking about. And we can also connect people based on similar profiles, especially for rare disease patients. This is highly relevant. They are looking to share experiences with other patients. Maybe they can get diagnosed faster if they can find people with similar profiles. So the sort of virtuous cycle we want to feed into is if we give the individual control over their data. So there we have the term data ownership, which I guess is a really tricky term to use in this room. So it's enabling people to act on their data subject rights, giving them control and access, even though we know it's a whole bunch of complex co-ownership. But we include the individual in this system. And we allow them to get better care because of their data profile. We also allow them to donate it to research, then they get represented into that data set, and the science that comes out of it is also better for them. So we want to fuel precision medicine, fuel life science research, so we work together with pharmaceuticals companies that they want better data sets. So we want to fuel precision medicine research by facilitating repurposing of health data, so that's a lot of data sharing with a privacy by design data sharing platform. So there was a lot of big abstract vision about what we do, and how we do this is with a super interdisciplinary team. So we have the CEO and co-founder Nima right there with a computer science background, and we have clinical and we have legal all in the team. So Nima started the company actually out of a personal experience. He has needed to move across a lot of different countries, and during that time didn't have access to healthcare. It was especially problematic for his parents. They have many different chronic diseases, asthma for example, and needing to be re-diagnosed every time to get access to medication really sort of sparked him to make a technical solution for this, sort of with the computer science mindset. Why don't we have our diagnosis with us? Why do we not carry this with us? So that's how it got started. I'm a researcher, background in genomics, and while I was doing my research, I didn't have access to the data that I needed, a lot of proprietary limitations. It took so long, I only got my actual data at the end of my research. So that also sparked some inspiration to maybe build a solution for this field instead of zooming in on one research area. We're all privacy enthusiasts. Mustafa is a cybersecurity engineer. Federated learning is also another privacy measure I will touch on at the end of the presentation. Then we have Hanneke, who's from the pharmaceutical industry, and we have Maria sitting right there, and she has studied digital technologies and law, which is like a really, and privacy law, which is a really interesting combination for us. So we're very happy to have all these disciplines in the team to tackle these super complex challenges, basically. So to get started, what is artificial intelligence? First I just wanted to sort of maybe clarify these terms. I think most people don't really know what's the difference between AI and machine learning and deep learning and large language models, and how do they relate to each other. So a little sort of zoom out. You have data analytics, which analyzing all data, and data is at the bedrock of AI. And AI is this giant field of study. And then a subset of AI is machine learning. And machine learning is when this AI can learn by itself. The machine can learn by itself. And then deep learning is a form of machine learning, but then it becomes a lot deeper. So the model is a lot larger. Instead of just a few layers or a small size or a few parameters, it is huge. And that makes it a lot more intelligent. And then we have generative intelligence, and that's what we're all talking about so much these days. Those are those large language models. They are generating, they look creative. It looks like they're creating something. They're creating text, they're creating images, they're creating music. And they are a subset of deep learning, because these models are really deep, they're really huge. I think that's what I said, yes. And this is an even more comprehensive graphic that sort of shows you all those different types, like artificial intelligence. You have reinforcement learning and speech recognition, and you have machine learning, for example, unsupervised learning, so it can learn in an unsupervised manner, no human intervention. All types of neural networks, deep learning, and generative AI, for example, large language models. When we talk about AI, we often talk about this very general, magical thing, but it's always good to realize which AI are we actually talking about? Because they all have different purposes and functions and use case and different risks associated with them. With that, I'm going to pass the mic to Nima, because he's going to give a little bit of a history about AI.
Thanks, Sara. Yeah, Sara already introduced me, so I'm not going to do that again, but I explained why I'm going to walk you through the history of AI, because I think it sort of gives this helicopter view of what we have been trying to achieve with technology and with mathematics and where we are today. And maybe looking past, we can make a projection of what future could look like, right? And I actually put the first slide on the 1950s, but it goes naturally way more back than that. I wish I could start, from way, way back. I'm a history buff, besides being a computer science nerd. So hopefully by combining these two, I can shed some light on why we're using AI these days. So who in this room knows Alan Turing? Nice, cool, that's almost the far majority. So he's been one of the geniuses who, for the first time, explained the concept of a machine learning by itself, right? His research already started in 1930s by explaining what is formal logic. So how do we go from mathematics and think of the circles that Sara just showed, right? So we have a lot of data, we need to analyze that, and then reaching to a point that no matter how many humans we throw at the problem, we just don't have enough time to solve all this problem together. So dreaming that there would be a machine that would do a lot of these calculations for us, right? This is pre-computer era. This was partly also fueled by Cold War and Second World War, having the need of being able to decipher what German Nazis were trying to communicate using sort of their cryptographic language and the whole Enigma machine. Who's ever here heard of Enigma machine? Right. I'm too young probably to ever know this, but this is important history, because sometimes it shows a lot of innovation is driven by a lot of larger, world level issues that we're trying to tackle. So after of course deciphering the Enigma machine, a couple of decades after, in the 1950s, for the first time we wrote a seminal letter talking about what can we do that these machines can start mimicking humans, right? So it was now after just solving the problems, but he already imagined how can a machine mimic humans. So he started introducing the Turing test. Anybody heard Turing test before? Right, so Turing test is this idea of, can we interact with a computer without actually understanding there's a computer behind the scene talking to us? And this has been a thing of like fairy tales for decades for a lot of researchers, mathematicians, computer scientists, that can we actually reach that day? And today, I think we can boldly say that has already happened, right? If you're interacting with just a chat system and nobody tells you it's a human or it's a customer service talking to you, it's becoming nearly impossible to sometimes tell that apart. So we have already achieved that, what Alan Turing one day imagined where we would be. So then what is the next big thing that we're trying to achieve, which is the artificial general intelligence, AGI, right? So making computers that are more capable of humans. Very scary thought, but hold that thought right there. Let's walk through the history a little bit more with me. We are at the point that AI can already be created. This was one of the parts. This is of course AI generated, if it's not obvious, the image on the right. And we thought that computers can at best maybe just analyze data and calculate and do computation, but anything creative, they're not ever going to be able to do that. Now we see already AI art surpassing a lot of humans, definitely me, because I suck at making anything artful in that sense. So I already told you about the 1950s, where Alan Turing for the first time asked this question of, can we actually make machines that would imitate human beings? Then we had in 1956 at Dartmouth that for the first time the term artificial intelligence was coined. If it's interesting for you, that's a really cool conference to look at the content. But there was this interesting era between 1956 to 1980s, 1990s, which we call AI winter. So what does this AI winter mean? It was at the point where we had come up with mathematical algorithms and formulas that can solve problems theoretically much faster than humans, but we just didn't have the machines that are capable of doing it. We just had physical limitations of how much transistors can we fit into a CPU, into a computer that can run all these machines. So we had surpassed theoretically, but the technology wasn't there. And this has been the case up until today, and seems to be still the case as well. We have already come up with algorithms today that can achieve much farther than we can even imagine today looking at GPT-4. We just don't have enough servers and infrastructure that can actually do those computations. We just don't have enough electricity to feed these machines, right? So we're still somehow bound by the physics of this world. That's, I guess, a beautiful message to take away from this part. So at the end of the AI era was when we had, for the first time, actually built machines that were strong enough. Let's jump actually a bit further. Let's make it a bit more about today, right? We are now all fascinated by GPT, ChatGPT of a technology. Where did that come from, right? So I'm going to break it down into what is general AI and narrow AI, but just to look at a bit history of the transformer models or language models. Are we talking about large language models? It was for the first time introduced in 2015 in the attention mechanism, when we learn that from text the computer can learn how to repeat the same text if it sees it often enough. So if you would be able to break down the human language into a computation representation form, if you can store it in some form of a database in form of mathematical numericals, right, from a language, from text going to numericals, then you can run calculations and make that repeated process so many times that the computers learn what to repeat, right? So the word there is repeated so many times, it knows how to create the there on its own in which part of the sentence. Of course, in the first version, it was really bad, but it was capable enough that caught the attention of a lot of people. So many of the people who wrote that first paper in 2015 and later the transformer models were the people who co-founded OpenAI, right? Which is sort of the parent company of the modern large language models that we see today, right? So there was a bunch of scientists who discovered something. It was so amazing that they were like, how do we bring this to a production level? It was the desire to go from theoretical and research and science to making a product that actually can touch people's lives. And you see in 2019 when GPT-2 was introduced, so this is before the ChatGPT era, we already saw applications who were built on this technology, and that sparked a lot of politicians' curiosity as well, which we heard from Dan, right? That already from 2019, they wanted to write these regulations, which in my limited understanding, it was partly also sparked by this fascination that, okay, we are now reaching a whole new level of AI, that it can get out of hand much faster than we thought, because so far whatever we had built before this era was narrow AI. So what is narrow AI? Part of that, I'm gonna get to it. We know AI already for a long time in application, right? I think we're all familiar with Siri and Google Assistant for a while. They were not really as capable as we hoped for, but they were close enough that continuously sparked our interest. Sara already mentioned Netflix, right? This is the recommender systems, meaning that they can see from your behavior that you like something a lot of times. It can learn how to recommend that to you, right? You can see it from commerce, for example. When you buy a product, it tells you, hey, you can also buy this product with it. So many people also bought that product with it. So how do you encode all of this human behavior into a computer representation was a fascinating era that we had during the Netflix, Spotify, and Amazon era. It's also in more mundane day-to-day tasks that we don't think about, right? If you just use Google Maps, it's not just a calculation, a mathematical calculation from this point to that point, how much is the distance, and run the calculation. It takes so much more parameters into account. How much is the traffic, what is the weather, right? It's like, what are the other shortcuts you can take? This won't be possible if AI wasn't already used in routing optimization solutions like Google Maps. We see computer vision solutions, right? If you use Google Photos or Apple Photos, it reminds you of memories that are similar to each other from over the years. Like all the time that I had pizza, like showing a series of photos of pizza to us, right? And these models have gotten so much smaller and smaller that can run on our own phones, or Tesla in form of cars that are basically on the road and can detect objects. But there are also more important solutions that have been implemented in the field of healthcare as well, like classifier models where they can detect there is a cancer, for example, in an image, already better than humans for decades, for a decade, not decades. So to sum up all that I told you, we can classify at a really high level all AI in two groups. Narrow AI is this specialized AI for very small single tasks that gets really good at it, and this is what we've been building already for decades, at least for the past 2 decades. Think of it like recommender systems. The general AI is what we were hoping to achieve, where one AI can be capable of doing multiple things. Right now, if you're using ChatGPT, it can both create an image for you, it can write programming code, it can do multiple different tasks. So this is something very new and still a lot to be discovered here. Sara touched upon machine learning, right? So AI learning from itself. How does that work? You can define it into 3 groups: supervised, unsupervised, and reinforcement. I don't want to go into too much detail, but what you can take into account in, for example, in supervised, you can provide a target, and I hope that the AI would reach this certain target, and you would train it so many times until it would reach that certain threshold. But not for everything you can set a threshold, so then you need unsupervised or reinforced. I would love to tell you all about this, but I don't think this is why you're here, but just sort of broaden the scope. And Sara's gonna explain to you about how to bring it to application.
Yeah, so thank you. One final part about how does AI learn that I wanted to highlight, and I think is very relevant for all the property IP lawyers here. Because it's a big difference with how does AI learn if we're talking about training the model or if we're talking about fine-tuning the model. So training the model, it's very expensive, is what these big open AI companies are doing. If you've seen their fundraising rounds, they raise like millions and millions and millions and millions, which is because they have to have so much data and so much computation power. So it takes a large unlabeled corpus. So corpus is the big data, and it's computationally expensive. So yeah, we rely on OpenAI or Facebook with their Llama model, that they do sort of the big pre-training work, and then actually what most people are doing is fine-tuning. And fine-tuning is much cheaper. You get a small labeled data set, and you sort of mold the existing model to your application. And with training, the data really gets embedded into the model. And with fine-tuning, the data does not get embedded into the model. So from IP point of view, that's also quite different. And also from a privacy point of view. So the data in here, sometimes it can leak out as well. There's this famous example from when ChatGPT came out. People were prompting it and they were just asking the same thing over and over again 1 million times to try to get it to give some weird behavior, and it did. Someone's CV just dropped out of nowhere, so that was quite a lot of personal information. So those are sort of the risks of, the training data gets embedded into the model, and it can leak out maybe at moments that you don't want it, so you need to pay attention what you put in there. With fine-tuning, the data does not get embedded in there like that. So that's a big difference. AI training, AI fine-tuning, and finally you have AI inference. Inference is a fancy word for actually like using it. So when you are giving a prompt to ChatGPT, you are inferring the model. So yeah, this may be a bit over complex, but if you look at training, you have a new data set that you give it a new capability. So in this example, you give it a training data set of cats, a lot of cat pictures. You feed it to this new model that you're making, and it sort of converts this just to numbers, and it has a numerical representation for this is what a cat looks like. And it's able to tell this is a cat, that's a dog. Takes a lot of data, but you can learn that. And then inference is using it. So I have a picture, is this a cat, yes or no? That's the inference. And the image that you use to say, is this a cat, yes or no, that doesn't get lost into the model.
But is it still processed in the sense of the GDPR?
Yes, so there is indeed a big difference between what happens technically and what happens legally. So if we're just talking about technically training, the data gets embedded, technically it does not get embedded into the model with inference, but still you are processing the data, right? And so there's definitely data processing there, so GDPR definitely applies. And if we're looking at sort of the legal measures as well, you have to see if you are inferring the model with, for example, OpenAI, with ChatGPT. Do they say that they will then also use the data you gave for inference? Will they also use it for training as well? Right, because they want to gather as much data as possible for their training. So there's that contractual obligation that you need to look at. Is the data that I use for inference also used for training?
Maybe if I can just jump in with one comment. You have to separate between the training phase and the usage of the tool as such. And taking ChatGPT as an example again, they break down the information into very small tokens of 4 characters. And those 4 characters are put together by an algorithm which is the most likely ongoing of the sentence. And those 4 characters in one token do not carry copyright protected information, do not carry personal data, because it's only 4 characters. And therefore this is how the developers of AI tools try at least to make sure that when the product is used by all of us, that we do not process personal data, that we do not process copyright protected works, because the puzzle pieces are so tiny that it doesn't carry that information that the law protects under IP law or personal data and privacy laws.
Thank you. So then I want to move to the next part, more practical. So this was a lot of theory to give a lot of context, but very practically, how do we achieve transparency and explainability, accuracy and robustness, and privacy and security? So what I wanted to do is actually show our product that is using AI on sensitive health data that we are currently running actually with clinics. To give the example, and it's a nice use case for large language models. So our product is called Eligible. It's eligibility screening for patients for clinical trial recruitment. And it has that little AI in the middle, which is, on purpose. So it's an AI-powered co-pilot for patient pre-screening for clinical trials. So we say co-pilot is an assistant to the humans, we're not replacing them, and they have the final decision making. So I have a little video just to show what it is. Let's see if this plays. Yes, it does. All right, so the, yeah. Okay, so imagine you are a healthcare professional, you're working in a hospital, and you get tasked with finding patients for your trial. You have to run that. They say you have to find 10 patients this month. So what usually happens is they look then at the clinical trial protocol, which is a lot of criteria of what these patients have to adhere to, and then they have to look through the patient records, which is very unstructured. 80% of this data is free text, PDF, so they have to read through like tens, sometimes hundreds of pages about these patients to try to figure out, do they match? Can I reach out to them and include them into the trial? This goes wrong a lot of the times. 85% of trials are actually cancelled due to the clinical trial recruitment problem. So that's why we also thought it was a good application to start with regards to how can we personalize healthcare. Clinical trial recruitment really seems to need it very much. It's really limiting drug development. So imagine you're this healthcare professional and you have your trial protocol. So that's what you're uploading. This is also a PDF. From a technical point of view, PDFs are quite unstructured and difficult to work with. This is what it looks like, specific criteria. This is what this patient has to adhere to, what they should and shouldn't have, which lab values, which diagnosis. And it's just sort of very difficult to check this as a human, because then you've done all the work and you checked most of them, and then it turns out that the last one are not suitable, and you can throw away all your work and you spend so many hours on this administration. This is the first step where the healthcare professional checks, all right, were all these criteria read out? This is already an AI reading it out of the file and classifying it on a pre-screening and a screening criteria. And the human can check whether the AI did it correctly. And then they can go to the next step, and all these criteria, they are like little Google searches into the medical database. Like a lot of Google searches that look through this super messy data, And this data is typically not very AI ready. It's really quite horrible how it's set up, but with large language models, anything is possible. And then you get ranked results. Which patients do we think are most likely to be eligible? So where should you start screening and evaluating? Then we explain the results. This test patient 10 seems to be 100% eligible. They pass the inclusion criteria, they pass the exclusion criteria. Sometimes we don't know, there's no data available. We try to explain the results really well to the end user so they can check what it's doing. And then there's the final step where they select the patient and see if they can include them. Let's see, next page. Yes. This is the final step. It also generates tasks. What does the healthcare professional still need to do to find out that they're actually eligible, and then include them into the trial. So that's the process that we're helping with. So how to achieve transparency and explainability in general, and how we do it in this tool. We have the AI literacy, so providers and employers of AI systems have to take these measures, so there's sufficient level of AI literacy, especially for the persons dealing with operation and use, so in our case maybe research nurses. They have to deal with these AI systems, and we have to bring it to their level of technical knowledge and education. Well, they weren't technically educated, so we find this quite challenging. How far do we go in explaining what is it that they actually need to know? How much do they need to know about the algorithm? And so it depends on which stakeholder you are, how much you need to know about the algorithm. And I guess it's up to many stakeholders and many conversations to figure out who needs to know what. If we dive a little bit deeper, there's quite a fundamental challenge here. And you can look at that with explainability versus interpretability. So explainability focuses on what are the decisions made and explaining that. And interpretability is focusing on the understanding of the inner workings of the model. So do you truly understand what the algorithm did? Can you explain step by step how it came to its decision fully? Or are you just sort of generally explaining the output while you don't actually know what's going on the inside? And the truth is, a lot of models we cannot interpret fully. It's a black box. We don't actually know how it really came to its decision. This is one schematic that shows that you have interpretable models, for example, decision trees. You can look at the model, you can see, if it's a male, then yes. If it's a patient above 18, then yes. And you can traverse this tree, you can see its reasoning. It's fully interpretable. But most models nowadays are huge. They are deep learning. They are these big generative models with 70 billion parameters. Sure, you can look at those 70 billion numbers, but it's not going to tell you much about the outcome. You cannot check all of these 70 billion parameters as a person and truly understand why it came to its conclusion. So even as technical developers, we cannot claim that we can fully interpret these models. So I think we were talking about explainability then. Explainability then is a huge field. How do we then explain how these models come to this conclusion? You use AI on AI. We have this a lot. This field is called XAI, explainable AI. You have many measures. So this is another thing that technical developers do, and us too. For example, you make a feature map. You try to find out what are all the features in the model. Or you try to give a model that mimics the model, but then in a simpler format. There are many ways possible, but the conclusion is usually you have to add another model to your model to explain the model. So we focus on explainability, not on interpretability. So we can say what is the input that was being used to give the outcome. Because there are tens of pages of patient data, but if we say this was the data used in the outcome, and then we can show that to the human, then we can explain how it came to its conclusion. So in explaining what we do, we have a lot of human in the loop steps for safety reasons. At this moment we have 3 human in the loop steps, just because we want to start out as safe as possible and gather as much feedback as possible. But it's kind of a trade-off. You want to automate a lot, and you don't want the human to do a lot of work, but also you want the safety. So yeah, there's always a trade-off there to explore. So probably in the future, maybe the first human in the loop step could be skipped in our case. It also ties very closely to GDPR compliance. You want the human in the loop because also you don't want automated decision making on these personal cases. And transparency is also dictated in the GDPR. In the final results, for example, we present a ranked list of patients. We don't say this is your patient, but we say this is your most likely patient. So we don't select ourselves, we let the human select. The final decision is made by the patient, by the healthcare professional to actually include the patient. And I think this is the most important part and the most challenging part of our algorithm. So this gives the results criteria by criteria. It's an inclusion criteria. The patient fails because their MMSE score, that's some kind of a medical score for Alzheimer's disease, it needs to be between 18 and 26, but what we see in the EHR data is 27. So the reasoning of the model says the patient's MMSE score is 27, which is outside of the required range. So we give the conclusion, we give the source data, and we give the reasoning, and we allow the end user to validate that. So we are transparent about it, we explain it, then they can validate and verify it, either with a thumbs up or if it's a thumbs down, we gather structured input, why was it wrong? Then we can continue learning and training the model. And this goes for so many applications. So yeah, I'm sure you'll encounter that in many other fields. Yeah, so that's, I think, all my learning so far about transparency and explainability. Then we have accuracy and robustness. Like I explained, large language models and AI in general, it will give different outcomes every time. But in some scenarios, like self-driving cars or medical devices, you need it to be predictable in a way. You need it to be robust. You need it to perform consistently very well. Which is challenging because small changes in input can lead to large changes in output. And the models that we rely on change over time. So we rely on ChatGPT or Llama or other big expensive models that these companies make, and we cannot work without them. But if they make an update, then maybe our entire system functions completely different. So what you can do, one of these robustness measures in this challenge is to use multiple models. So you don't just use one. No, you ask the same question to all of these different models, and then you've engineered it such that they all give the same outcome. And then one day they make an update, and then the results of that one model start becoming different. You detect that, then you know, oh, there's something up there. So that's how you can really sort of strengthen the robustness of your system. Also called redundancy, I guess. But yeah, so you evaluate the similarity of these answers all the time. It's like constant monitoring. Again, we're talking about many parameters here. So this is like the mathematical methods that you use to evaluate the similarities of the output, called cosine similarity measures. Yeah. And then the final cherry on the pie challenge is how to achieve privacy and security. So yeah, we already talked about data leakage into models, which is important to address. You address this with contractual agreements and with technical mitigation measures. So for example, when you're working with a model, realize is it open source, which has the advantage that you can host it on your own premise, it can be completely within your control, or is it closed source like ChatGPT, so it's proprietary and you don't actually have control technically over what they do with your data because it's not hosted in your within your premise but somewhere else. And yeah, so another measure that we do to is we actually minimize the data that gets into the model before we use it. So we do this pre-screening algorithm that I showed, where we input very sensitive patient data into these models, and out we get this eligibility report. But before we do that, we de-identify and pseudonymize the data. And that's the technical measure that we do, and then there are a bunch of legal measures, like we have very strict data processing agreements, we have like a human-in-the-loop inspection, was the data actually de-identified well enough, and then at the end we make sure that the patient data can also be fully deleted. And this is what our de-identification demonstration looks like. So patient records, they are like a special type of data, also PDFs, which again, horrible data format if you're a technical person. And yeah, it contains like PSN numbers and birthdays, patient numbers. This is Nima's file, he broke his nose. So that's what
3 times.
And yeah, this is what you can see. It detects all these fields and what it is. Like, is it a personal name? Is it a postcode? Is it a birthday? Is it a BSN? And it detects the difference between a birth date and a regular date. And that's what you again need AI for. Like, you cannot, something just rule-based, a simple algorithm doesn't capture this, because it's so sensitive to know the birthdays of patients. And what we do is we recode that to like something more approximate, like a birth year. But we need to know exactly at what time, at what day they started their medication. So we cannot just remove all dates. So that's what we do first, is remove all that data, and then we have a specialized model for healthcare data like that. So it's always layered, right? So we have a pseudonymization policy. It's always a trade-off between privacy and utility. What can we remove? What can we keep? What do we need for purpose? So this is like specific pseudonymization policy for our use case, where we layer technical measures and legal measures. So that's all about the current product that we're deploying. So if you have clients that work with patient records and want to apply AI, we can maybe leverage this DID tool as well, or just maybe advice, because we spent quite some years thinking about all the privacy problems in healthcare. And yeah, we don't stop there. We also perform R&D on the privacy for genetic data. That's the most sensitive. So this addresses the more general problem of what if you want to train a model to gather on sensitive data? So you can mitigate a lot of risks by doing just fine-tuning instead of training yourself. But what if there's no way around it? You need to create a new model. You want to train a new model, but you need a lot of data. So you need to collaborate with parties. You need to agree on where you're going to move the data to. And sometimes that's just not possible. And that's the case with the clients that we work with. Genomic researchers, they have DNA data in their institutions, and they cannot move it off the premise of their institutions, let alone across country borders. And they really need to collaborate on it because they also want to use AI. And that's why we made a framework. It's a federated learning framework. I don't know, who has ever heard of federated learning? All right, we have four people in the room. Okay, so like brace yourselves, it's quite technical, but what it comes down to is, since I've been working at a startup, I've learned a lot more like engineering things. Like I have like a half engineering background with my studies nanobiology, but the team that I work with is much more technical, and I'm just in awe with what's possible with cybersecurity techniques. So we can still use and access data and compute on it without us having to see it. So it's like under the GDPR, you would say, oh, this is a strong technical measure, for example. And when you're working on a special data class like genetic data, that's where you really want to apply this. So we assume that genomic researchers, they want to collaborate on super sensitive data, but they cannot move their data off premise, so they want to use a federated learning. And what that is instead of moving your data to one central hospital to aggregate it, you keep the data locally, and you distribute the computation. That's maybe quite complex, but the thing is you don't need to move the data to still perform your algorithms.
You share the learnings, not the data. That's
Yeah.
the principle behind it, and you can decentralize to allow the system to learn decentralized.
Yeah, and sort of what we take on as our sort of function as OASYS Now is we are very interdisciplinary, so we try to translate between the technical solutions and what the researchers need, what the legal departments need to know, what the IT departments need to know, because this is such a promising solution, but it's not that widely used yet. So we have found that IT departments find it really difficult to implement this technology in a secure manner. That's the challenging thing with cybersecurity is always, it can be a beautiful technology, but if you don't implement it watertight, it's useless. You can see cybersecurity always like defending like a castle. You know, you're defending this this data pool, and if the window is open, then it's great that you have like thick walls, but then they can just bypass that. So that's always the thing with cybersecurity measures and legal measures for that matter. Like you always layer them, and you need as many as possible and make sure that there's no open doors. So yeah, for regular overworked IT departments in hospitals, this is quite challenging to implement that correctly. Then we have the legal departments, also quite overworked in these healthcare institutions, and they need to verify the compliance of this great security measure that they don't actually know how it works, so how can they sign off on the risk mitigation? So yeah, that's what we try to address to really bring this amazing technology that we see, bring it to practice. Yeah, and then the interesting setup that we also have is that, yeah, these hospitals, they work together, they usually trust each other, but still there are some limitations. But they usually don't trust cloud providers or IT companies like us, because they're like, yeah, what do you want from me? You're commercial, you're technical, how can we trust you? And that's sort of what we build into the security layer is a way that we never have to see the data that we work with. So we can prove in a technical manner that we can be trusted, and then we can receive more certificates on that to show in a legal manner that indeed that's true. So yeah, that's what we've built. It's together with NVIDIA, which is sort of all the, like Nima already touched on it, AI runs on computers, of course, and these computers are made by certain companies. NVIDIA is the supplier of the computer power necessary for AI. And they have this federated learning framework. We built an implementable framework around that genomic researchers can readily use. And we developed and illustrated this together with the Erasmus Medical Center. And that's called confidential multi-party AI. Data stays on-premise. You have verifiable security against data leakage. So the genetic data that's being shared and learned on, these parties never see it. You know that data doesn't get leaked. We never see it, but still, in the end, you have a model that you created together. Yeah, explicit trust through technical means instead of implicit. So it's not, yeah, we like each other, so we trust each other, but you can prove that, yeah, there is no meddling with the data or using it for something else that wasn't agreed on. Verifiable compliance, yeah, we try to certify different parts of the technology, so the people who have to sign off only have to sign off on the super small part and not on, yeah, the super big part. So that's our R&D side, confidential federated learning. If you want to know more about any of these like security measures, either for healthcare or for a different field, I would be happy to chat. So yeah, that's what we covered. OASYS Now, what is AI, how to achieve all these things. And yeah, and the solutions that we have is on-premise de-identification for pseudo-anonymization for super unstructured data. So far it's only been done on like tabular data, which that's easy. You just remove sort of the whole column with all the names, but on unstructured data it's challenging. Eligible, so we're able to leverage LLMs to match patients to trials in a data-driven manner. Previously, right now, this is not a data-driven process. And we have R&D on how to handle super sensitive data types like DNA. So yeah, that's what we are working on, and hope that we can exchange good ideas about how we can make this field more privacy forward in a technical way as well as a legal way. Thank you. Yeah, are there any questions?
Yeah, I have a question.
Yeah.
Thank you for the presentation. I come from the financial sector. So in the financial sector, as you may know, we've had this initiative called Transaction Monitoring Netherlands, which is killed. I see some similarities here. And my question is, how do you make sure that society accepts this? Because this is what we experienced with Transaction Monitoring Netherlands. The 4 banks in the Netherlands were extremely happy, were positive, started a company, started to exchange data anonymously, and in the end, politicians, but predominantly society, didn't accept this. There was a lot of criticism, there was a lot of spinning going on, and in the end, the banks retrieved.
Yeah.
So how do you convince, first of all, hospitals, but most of all, I would say society in general, to go along with this?
Yeah,
That's what I missed a little bit in the presentation, to be honest.
Yeah, no, very, very good point indeed. First of all, it's very interesting that you come in it from the perspective of the financial sector. We look a lot at the financial sector, and we've seen the digital revolution that has taken place there, and that kind of technology and those classes indeed are very similar, and we basically want to bring those to healthcare. So that's a very fair parallel indeed to spot. It is indeed, it is the main challenge, how to convince people to use these tools, because it's new technology that they have to trust on for their security. And I think that's also my biggest learning in the past 3.5 years that I've been working with Nima on this, is how do you talk about privacy and security with people? How do you talk about their sensitive data? Because usually if you bring it up, people just run screaming because they're like, no, I don't want anything to do with this. But yeah, our approach is very bottom up. So instead of us being like a large pharmaceutical company that's deciding like, this is the way we're gonna do it, now we're gonna set this up. We are a startup that's starting with the patients. We are patient first. We engage with them and we make sure that it always benefits them. So we have a large network of patient organizations that we work together with that give input on how we design our solutions that they ultimately benefit them. Then we do the same with hospitals. We also work there bottom up, working our way up to talk with the privacy team, the IT team, the end user, the nurse. So it's a super complex stakeholder environment, and we have to talk with everyone to make sure that it meets their needs. And then it's about translating all this technicality to things that people can understand, because they cannot understand federated learning, but they can understand that we got a European award for cybersecurity from the European Lighthouse for Safe and Secure AI. It has a good name, it has 10 top tier professors associated with them that are trusted in the field. And so like everything with trust is, okay, they trust you, so I trust you. So it's about building up this network of trusted people. Certificates, GDPR compliance certification, ISO certification, and we do that in a live way, so not in a static one-time audit, but we are monitored real time. So here we also use technology to show trust. We speak a lot at events, and we got that data privacy award. So if people don't understand anything about privacy, we're like, look, these important people in the Netherlands, they gave us an award, they know. So yeah, it's all we work on, and we try to show that in every part. But it is highly challenging, and you have to adapt the story depending on who you're talking to.
But Tom, there are 3 methods in principle that work also in the financial sector. Either it's, as you said, certificates, it's an audit being run by an authority which then gives you the nod of approval, or you get sued and you win the case. The last one is the most risky one because there's a period between being sued and getting the judgment, but it's probably also the best one to show, look, this is the judgment, it's in my favor, I'm clean. But those are, in principle, the three methods to get, yeah, the nod of approval.
And in my experience, it also has to do with momentum sometimes.
Of
Within
course.
healthcare, especially, we have the e-overdracht that is a main priority of the ministry at this moment. So sometimes it has to do with what you do at which time, and the timing has to be perfect.
Yeah.
So I fully agree. I think I'm very happy with the question, and I think it was really fantastic presentation. I'm super impressed,
Yeah.
and at the same time